Anyway, we have two speakers who will give a talk jointly on cutting rectangles into two congruent pieces. As usual, please mute yourself unless you have something to say.
Okay, well, thank you for the introduction, Doron, and for the invitation. It's always nice to be back at the experimental seminar that I spent 4 or 5 years organizing as a grad student. It's maybe the best seminar in the world, if I do say so myself. So today, it's especially nice to be giving this joint talk where I hope we will get the downsides of both speakers and the upsides of neither. Wait, sorry. We want the upsides of both speakers and the downsides of neither. Well, we'll see what we can manage to do. So we want to report on some progress on a nice combinatorial problem that we came across earlier this year. It has to do with, how I've been explaining it has to do with graham crackers. Let's see. So imagine that you and a friend were trying to share a graham cracker, and maybe you're like a small child, so you're very finicky and particular about this. So you want to take a graham cracker and split it into two pieces, and the two pieces need to be identical. So it should be fair. You should have the same amount of graham cracker, but you don't want your friend to have a prettier piece of graham cracker than you. So the two pieces you break it into should be congruent, actually. They should be literally the same up to some kind of rotation and reflection, something like that. So we'll represent a graham cracker as just some rectangular grid. And here are some ways you could break up a 2 by n grid into two congruent pieces. So you could break it just perfectly in half, the top row and the bottom row. You could do some kind of L shape, something like that. These are all valid ways to do it. And the obvious question is, how many ways can you do it if I specify the shape? I give you an m by n rectangle. You say, how many ways can you break it up? And some important things to mention. So here are 6 examples, but we would really only call these 3 different examples. Because if you think about it, everything in the bottom row, the bottom 3, these are just reflections of the top 3 or rotations or something. They're not really a different way to break it up. They're just a different way to draw it. So we're going to exclude double counting symmetric arrangements. Now, we heard about this problem earlier this year from this very nice article in this French magazine, Pour la Science. Jean-Paul Delahaye wrote this article where he asked this question, not about graham crackers, it's just about rectangles, though. He said, if you have this rectangle, how many ways can you divide it into two congruent pieces? And he specifically talked about 2 by n and 3 by 2n. So 2 by n turns out to be relatively easy. It's kind of straightforward. 3 by 2n turns out to be quite a bit harder than 2 by n. And what we want to talk about today is how you do the 4 by n case. So he did 2 by n and 3 by 2n, and when we asked him, well, how could you do 4 by n? Is that possible? He said, it's too hard. We didn't even think about it. So today we want to walk you through a little bit of how the 3 by 2n case works to get you familiarized with the problem, and then talk about how you can do the apparently a little more difficult 4 by n case.
Great. So when he counted the 3 by 2n rectangles, he got 2 to the n plus 1 minus n plus 1, which is a very nice, simple formula. A little more complicated than the 2 by n, which is n over 2, but still very nice and simple. And the way he did this was he broke it up into 2 separate categories. There was sans crochet and avec crochet, without hooks and with hooks. Where the difference is that in the avec crochet, you have this overhang happening here in the yellow, and, the similar one happening down here in the blue. And in sans crochet, you have no overhang. It looks more like 2 pieces of a key. So these are the 2 categories. Let's look at them one at a time. We'll start with sans crochet. Sans crochet, he categorized by looking at the bottom row. You can either have the entire bottom row be yellow, or you can have all but 1 square of the bottom row be yellow, or you can have all but 2 squares, all but 3 squares, etc. We'll stop at n because once you ask for less than the left half of the bottom row to be yellow, you might as well switch the yellow and the blue and flip it over the y-axis, and you'll get the same thing. So these are the characterizations that he broken into, and then we'll look at one particular one. For example, all but the last a squares of the bottom row are yellow. So here we have a equals 2 in a 3 by 8. So we have 8 yellow squares and 2 blue. That means that to have a congruent piece, we'll have to have 2 yellow squares in the top row and 6 blue. And then when we remember that we live in the sans crochet, no overhangs category, that means that the first 2 squares of the middle row must be yellow, and the last 2 squares of the middle row must be blue.
Hey, Natasha, can I ask something?
Yeah.
Anyone who knows this stuff is going to be using Burnside's lemma, right? Are you deliberately not mentioning group theory in this? Counting orbits. You're counting orbits, right, under a group?
We are counting orbits, but I am presenting the proof as it was presented in the article, where they use...
But really, I mean, you shouldn't do this sort of stuff at the ground level. You should do it using group theory.
We don't want to say Delahaye doesn't know his stuff. I'm sure he's a very smart guy. But we thought this was a very nice elementary version of it, I suppose.
I don't think the Burnside's lemma is relevant here. It's too simple. It doesn't have much in this case.
Well, it's you want a number of orbits, right, under a group.
Yeah, trivially, but I don't think in this case the group is so simple. I don't.
It's a good question.
If you can do it without group theory, why not?
Okay.
Well, if you can do it with group theory, it's better.
Okay, it says on.
I think in both the 3 by 2n and the 4 by n case, at least for me, it is easier to control for symmetries ahead of time rather than counting the different amounts under different orbits. No promises. I'll continue. Okay, so we have these 4 squares left that we need to count the number of ways to fill. But remember that we only want to fill in the left half, because once we've decided on the squares in the left half, the right half will follow by the fact that the blue and yellow pieces need to be congruent. And so that means that when we choose the left half, that's 2 to the n minus a choices. Right, n is 4, a is 2, that's 2 squared, correct? We chose the left 2 squares, and that gives us choices here.
Is that not a vec?
This is sans crochet.
But
no crochet.
It looks like there's a hook.
So when we say hooks, we mean vertical overhangs. So here we'll see avec crochet in a second, and I'll point it out. Great. So this is true unless a equals 1, in which case we only have 2 to the n minus 1 choices, because now we'll do, instead of using group theory, we'll account for the symmetry over the y-axis by insisting that the first square in the middle row be yellow. Okay, so now avec crochet. Avec crochet has an overhang. So the way that he characterized avec crochet divisions is by specifying a thickness of the left wall, followed by how many squares there are in the overhang. So here we have a thickness of 2 and an overhang of 1. Right, so that specifies exactly how many yellow squares are in the top row, which means the rest of the top row must be blue, and the bottom row, again, must look kind of the same in that same number split different colors. So we have those 3 yellow and the remaining 7 blue. And then because we want to make sure that we have that overhang, under all C yellow squares, we're going to put blue squares, and then on top of the C blue squares on the bottom right, we'll put yellow squares. So here it is, our crochet going this way. And then we want to make sure that our pieces are connected, so we can't have that blue square all by itself, so we'll add those in. And now, like with the sun's crochet, we need to fill in half of the remaining white squares. We have 2 to the n minus b plus c plus 1 ways of doing that. In that case, that's just 2. Here's one of them. And putting this all together, we get the number of cases that are sans crochet with a equals 1, plus the sum over all a sans crochet, plus this double sum over b and c of avec crochet, and Maple will verify that this simplifies to 2 to the n plus 1 minus n plus 1. And the reason that then this does not extend is to 4 to the n, to 4 times n, is this question of what do we count as avec crochet? All of these examples have some kind of vertical overhang, but they're very different, and it's not easy to see how you would split it up into these cases.
Okay, so the way that we thought about the 4 by n case is, first of all, we got tired of using ticks everywhere to make colorful pictures. So we translated everything into binary matrices to make it a little bit easier on our fingers. So I'm going to give these things a name. Rather than think about the colorful pictures, I'll think about binary matrices, and I thought we could call them graham matrices, if you don't mind. First of all, because I started talking about graham crackers, and second of all, happens to coincide with Ron Graham's name, so we can say we're naming these after Ron Graham. So we'll have a graham matrix is an m by n binary array, so just zeros and ones, where the zeros and ones will form exactly 2 simply connected congruent regions. So no holes, they've got to be the same up to rotations or with rotations and reflections, and the connectivity is just grid connected, so up, down, left, right. And we'll say that 2 Graham matrices are actually the same matrix if you can get from one to the other by reflecting them, rotating them, swapping zeros and ones, anything like that. So just a one-to-one translation from the colorful rectangles to the matrices. So the way that we thought about this problem is we said, why don't we give up on enumerating the Graham matrices? Just give up on finding a formula to add together like we did for the crochet trick. And instead turn it into something of a decision problem, where rather than count them, we just want to be able to, given a matrix, decide whether or not it is a Graham matrix. And the specific setup is we want to write some program that will read in 1 column at a time of our matrices. And once it's done reading in 1 column at a time, it will tell us, yes, this is a Graham matrix, or no, it is not a Graham matrix. That's what I mean by turning it into a decision problem. And the reason that you might try doing this is because it turns out sometimes when you solve a decision problem, you at the same time solve the enumeration problem in certain cases. If I borrow some language, I've been hanging out with computer scientists lately. They've been giving me free lunch over in their department, so I've been talking to them a lot, and I've been learning some of their words. So when computer scientists talk about these kinds of decision problems, sometimes they talk about parsers. So what I mean by that is a parser is a program that reads in some strings and decides whether or not the strings belong to a language. So your language might be specified, functionally by the parser, like the parser says what's in the language, what's not in the language, or it might be specified by some kind of grammatical constructions. Maybe you can write down some kind of syntax tree or rules, replacement rules, things like that. And then your parser will read something and say, yes, this is in the language, no, it's not in the language. So this is kind of like a decision procedure. You read something and you say yes or no. Now, parsers can scale in complexity. There's lots of different kinds of parsers that can parse different kinds of languages. The most general case would be saying you're allowed to write any computer program at all. Maybe you might say you have like a Turing machine or something like that. And then you can detect lots of things. Anything that can be detected by a Turing machine. All right, that's kind of anything you could think of writing down, basically. But if you can do that, you don't actually get any enumerating information. Okay, you can detect it. So what you want to do, though, if you can nail your parser down to less and less generality, you have a weaker and weaker parser, the more restrictions you put on what your parser is allowed to do, the more enumeration information you can get out of it. So the very bottom of the hierarchy that computer scientists typically, I guess maybe Chomsky is the one who really came up with this hierarchy. But at the very bottom of the hierarchy are these things called regular languages, which are languages that are matched by regular expressions and a few other things. If you can write a parser for your language that turns out to be a regular expression, then you can actually explicitly construct a generating function for the number of words in your language of a given length. That generating function is guaranteed to be rational, and there are algorithms to construct it exactly, typically fairly quickly as well. If you scale up and you can't write a regular expression, there are other things you can do. If you can do a context-free parser, then you get not a rational generating function, but algebraic generating functions, and there are algorithms to write down equations that they satisfy, things like that. But the basic idea is we thought, well, maybe we can write some kind of parser that's sufficiently simple that will give us generating function information. Still haven't said Burnside anywhere. I don't know if that's going to come up, but we were thinking parsers, not so much counting orbits, I guess. So let me talk a little bit more about this whole regular language thing. So like I said, the reason that something is called a regular language, if you're familiar with this, is because they are matched by regular expressions. That's one way to define them. But another equivalent way to define them that comes up a little more often in combinatorics would be a regular language is a language that is the accepting language of a deterministic finite automata. Okay, or DFA for short. So what is a DFA exactly? It is a finite graph that operates in a way on strings. What it does is it reads in a string one symbol at a time and uses the symbols that it reads in to conduct a walk on its graph. So you read in symbols, they tell you a walk on a graph, and when you're done walking on the graph, you look at where you're standing. What vertex are you standing on? If you're standing on what's called an accepting vertex, then the DFA says, yes, you're in the language. If you're standing anywhere else, you say, no, you're not in the language. So this is what a DFA does. Here I have a relatively straightforward DFA. What this does is it works on strings composed of any numbers of A's and B's. So you can read in as many A's as you want, as many B's as you want, and they determine walks on this graph. So the vertices are labeled 0, 1, and 2. The square vertex represents that it's a start state. The green vertex represents that it's accepting, and orange means it's rejecting. So what happens here, you start at vertex 0. Every time you read in an A, you increment the vertex counter by 1. Until you get to 2, then you loop back to 0. So you're counting the number of A's mod 3 is what you're doing. And you don't care about the number of B's. The number of B's means nothing to you. So this DFA accepts strings that have any numbers of B's and exactly 2 mod 3 many A's is what it does. So these are the kinds of things, this is one kind of thing you can detect with the DFA, these sort of fixed modular conditions. So this is the kind of stuff that you see in regular languages. So what we want to do is some setup like this, where we read in our matrices one step at a time and construct some big DFA that will tell us, is our matrix a gram matrix or not? And the reason for that, the upshot, the way that you get the enumerating information out of this is that if your language happens to be detected by a DFA, then words in your language just correspond to walks on a graph. And counting walks on a graph is a very straightforward, well-known thing to do. If you have some adjacency matrix for your DFA and you want generating functions that count walks, then you form this symbolic inverse here. And this gives you a big matrix of rational functions, and these rational functions tell you how many ways can you walk from one vertex to another on your graph. in whatever number of steps that you want. And this was our recipe. We wanted to construct a DFA that will recognize the Gram matrices, then compute some symbolic inverse that will give us the right generating functions, and then you add up the entries that you want. You actually say, okay, you started here, you ended there, and that'll be our generating function. So if you're more familiar with combinatorics, you might have heard this called the transfer matrix method, in which case it's a little more general. You can count like weighted walks on a graph. You put some other things in the matrix, but it's the same basic idea. You're counting walks on a graph. So the method is very nice when it works, but there are some problems with the method that make it difficult to apply sometimes. So this is all conditioned on if you have a DFA that accepts your language, then you get all these nice things. But how do you know that there's a DFA or not? That's the hard part. So it is famously kind of difficult to tell if you have a language, is it a regular language or not? How do you know if your object can be recognized with a DFA? I mean, after all, we're talking about some matrix and we want to know connectivity information. Isn't connectivity somehow like a global condition? Don't you need to keep track of how could you possibly do this with a finite amount of information? Even if you think that you could write some program to do it, it's not obvious if a generic program can be turned into a DFA. This is, I think, maybe like actually impossible to do in general. There's no way to do this for any potential program. Even if you know that a DFA has to exist for some hand-wavy reason, you can say, oh, I'm pretty sure one exists. That doesn't mean that it's easy to actually write it down and figure out what it is. And merely knowing that one exists is not helpful. If you really want concrete information, you have to be able to write down the adjacency matrix or some equivalent representation. And even if you can write this down, the matrix might be so big that the symbolic inverse is too difficult to compute. Might not be feasible to actually do in some amount of time. If you have, 10,000 states, depending on the density of your matrix, you may or may not be able to actually compute this inverse to see what you're looking at. But this is where things stood when we saw the problem at first. We thought, okay, 4 by n. You can read in one column at a time. Maybe there's some DFA. Maybe there's some grammar we can write down. We know there are these problems, but maybe we can overcome them. And that's where we were when we started thinking about the problem a few months ago.
So while Robert and Dr. Z went to try to, empirically count these for small values of n, I sat down and tried to, on pen and paper, write out what the grammar is. So Gram matrices, this rule about congruent pieces, can really be simplified to this complement rule, where we say that ijth entry is equal to 1 minus the n plus 1 minus ith, n plus 1 minus jth entry, which sounds a little complicated when you get the indexing right, but all that really says is if you reflect both vertically and horizontally, then the square you went to must be the complement of the square you were at. So this rule tells us that when we go through and input our matrix column by column, we only really need to fill in the left half. Once the left half is filled in, this rule allows us to fill in the rest and guarantees the congruent pieces part. Now we just have to deal with the fact that they need to also be connected. So here are the possible columns that we can have. You'll notice there are 2 to the 3 of them, not 2 to the 4 of them. And that's because, like in the 3 by 2n case, we're going to insist that the left half of the bottom row be all zeros. And so that fixes the bottom element of each column to be 0 and eliminates half of our columns. That's pretty much, in essence, going to be the states of our DFA. So, okay, we have some states. Which ones can follow which other ones? Some adjacencies are easier to see. For example, a column of all zeros can be followed by anything that starts and ends in a 0. This isn't everything it can be followed by, but it certainly can be followed by anything that starts and ends in a 0. And the column 0, 1, 0, 0, well, this can be followed by 0, 1, 1, 0, because the ones line up and are connected, and the zeros are, well, they're not connected, but they're as connected as they were. If you have a 0, 1, 0, 0 column, hopefully your zeros were already connected. And so adding another column with zeros connected to the ones you had should mean that your zeros are also still connected. However, 0, 1, 0, 0 cannot be followed by 0, 0, 1, 0, because here the ones only touch each other corner to corner, and we said that we want connectivity along the edges, along the grid, and so there's no way to fix those disconnected ones. So these are some easy adjacencies to see, but some are a little harder. For example, here with 0, 0, 0, 0, 1, 0, 1, 0, the zeros are connected like promised, but the ones now look disconnected. And that's certainly not something that got fixed in the past. But in this case, it can be fixed in the future. For example, if we just say that that's the left half of our gram matrix, then the ones do end up connected. But we could also mess this up by following it up with a column that goes 1, 0, 0, 0 instead of the right half. So to adjust for this, we said, let's have 2 states for the 1, 0, 1, 0 column. One for the zeros are already connected, but the ones are still disconnected. And one for the zeros are disconnected, but the ones are already connected. So adjacencies with that fix got handled. We have connectivity from that. Now we just need to decide on starting states and accepting states. Starting states, well, if we have all of the zeros and all of the ones connected, that's fine. If not, there's no way to fix that later. And so we only allow, that rules out columns 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, and 1, 0, 1, 0. You'll notice there's one more grayed out column, 1, 1, 1, 0, and we gray that out and don't allow it for the same reason that in 3 by 2n, we insisted that the leftmost square of the middle row be yellow. We're going to say, well, anything that starts with a column of 1, 1, 1, 0 ends with a column of 1, 0, 0, 0, and so we'll have already counted the reflection of it. So ruling that out, we have 3 starting states. And now we think about accepting states. If it is odd, then when we go to fill in the right half, the very edge of our right half is already filled in, which really corresponds to the fact that if n is odd, then the complement rule applied to the middle column says mi n plus 1 over 2 is equal to 1 minus m n plus 1 minus I n plus 1 over 2. And these are elements in the same column. What this means in a picture is that the middle column needs to be its own complement's reflection, and the only 2 columns that satisfy that condition are 1, 1, 0, 0 and 1, 0, 1, 0. When n is even, we no longer have the line of reflection or pseudo-reflection going through the middle of a column. It now goes after the edge, so we can just draw out all of our options and see which ones work. You'll notice that the first, 5th, 6th, and 7th have the ones and zeros all connected, so that's good. the second, third, and last, the ones and zeros look disconnected, but if we assume that the zeros must have been connected to get here, then the ones will be connected afterwards on the right-hand side as a property of the complement rule again. So that's all fine too. What doesn't work is this middle case here, the fourth one, where the ones are only touching each other corner to corner. That's just not fixable. So that's the only state that always rejects. So all of this put together, we have a DFA, much prettier than my original drawing of it. You'll see we have 9 states, 1 per column, with 1, 0, 1, 0 having 2. As in the simple DFA, start nodes we denote by rectangles. Green means accept, orange means reject, and we're using purple to say accept, but only if n is even. So here it is, the DFA. Everything was great. One small problem. We got an email from Gabriel Gendler, who pointed out that we counted both this matrix and its reflection. You'll notice I switched back to blue and yellow. That's because, at least for me, it's easier to see reflections when it's colors rather than numbers. So here it is, blue and yellow. We counted both of these, even though they're reflections of one another over the y-axis, and both of these, even though they're reflections of one another over the x-axis. It's fixable. It's all fixable. Everything's fine. So this reflection over the y-axis problem, this double count happens only when the first column is 1, 1, 0, 0. It's because we accounted for when the first column and the last column are different from each other, but when they're the same, we didn't ensure that the inside was controlled in any way. So this is fine. We fix this by saying we'll create a second version of the 1, 1, 0, 0 state and make that the starting state. And that one can only be followed by itself and 1, 0, 0, 0, but not 1, 1, 1, 0, which the normal in the middle 1, 1, 0, 0 state can be followed by. And that means we'll accept the left picture, but not the right picture. Great. Easy fix. All right. What about this reflection over the x-axis? Well, this happens only if the accepting state starts and ends in 0. So if we have exactly half yellow and half blue on both the bottom row and the top row, and that can only happen if n is even. So it's a little harder to fix, but that's okay. We'll say, let's stop accepting things that start and end in 0 in general, and we'll just construct a second component to our DFA that includes only these states that start and end with 0, and we'll force to say, if we're staying within these 4 states and not using any state that starts with a 1, we'll force the second state 0, 1, 0, 0 to appear before the third one, 0, 0, 1, 0. So we'll force this column to appear before this one, and that means we'll reject the picture on the right and only accept the picture on the left. These changes implemented. Here is our updated DFA. You'll notice, as I said, we now have 2 1 1 0 zeros, the original one, which is no longer a start node, and a separate one, which is just the start, and it connects only to 1 0 0 0 and itself. And then we've said in the original bigger component, reject always if you start and end in a 0, and we'll have a second simpler version for just that. Great. Everything's fixed, except for squares. Squares are a problem because unlike rectangles, which you can only reflect over the x-axis and over the y-axis, squares can be reflected over their diagonal. So Gabriel also pointed out that when n is equal to 4 and we have the same number of columns and rows, we double count reflections over y equals x. But n equals 4 is small, we can just count all walks of length 2 and then double them by hand and ensure that we get all of the pictures. So here they are, and each of these squares corresponds to 2 separate walks, one that looks like the picture we drew, and one that looks like the reflection over y equals x of this picture. So that we can just fix the value for, replace the 12 that we predicted with the 6 that we actually get. Easy fix.
Yes. Thank you, Gabriel, for giving us some extra work to do before this talk. It was very nice to make sure we were right, We really appreciate it. Now that you've seen how the grammar works, we thought it would be nice to actually show you something about the generating function that comes out and talk about how we think we could generalize all of this. So the grammar, as you've seen, is kind of annoying to get right. We didn't get it right, in fact, but then we did. And when we got it right the second, okay, you have to think, you have to do this and that. But at the end of the day, the DFA is not that complicated. So here's what the adjacency matrix looks like for the DFA. It's kind of puny in the grand scheme of things. It's only 15 by 15, and in fact, it's like quote unquote 15 by 15, because if you think about our DFA at the end, we really have a disjoint union of 2 different DFAs. So this is really a block matrix. Okay, so it's kind of 15 by 15, but really in practice smaller. So you can compute all the symbolic inverses that you want of this in, a second or 2 at most, even on a bad computer. This is no problem at all. Now, that doesn't mean that the entries turn out to be nice to look at. If you compute this symbolic inverse that gives you the generating functions, you get some matrix of rational functions, but they're pretty big, too big to show on a slide, so I won't bother showing you the full thing. But to give you a sense of how complicated, or not complicated, the things we're working with are, here's the LCM of the denominators of all the things in that matrix. It's some polynomial of degree 9, which is kind of like an upper bound on the complexity of our generating function at the end of the day. With one minor caveat. So this is not actually the denominator of our generating function. If you remember, the idea here was not to read in a column for the entire matrix, like one column at a time, but to only read in the first half of the matrix. So the walk on the DFA only represents half of the matrix. So if you want to get the sizes right, you've got to replace all the x's with x squareds, more or less, and some other things. But let's just say that you have to replace all the x's with x squared, so you go from half the size to the right size. In that case, you get a slightly more complicated denominator. Now it's degree 18 instead of 9. And any generating function that we cook up from this DFA will have a denominator that divides this. So this really is an upper bound now. Any sequence that we come up with will satisfy some recurrence of order at most 18, something like that. So this is not so big at the end of the day. So you can take this and you can work through the details and you can cook up this generating function. You figure out which entries exactly correspond to the start states and the accepting states, and you add them up, and you're careful to track this even and this odd business, and you do it all in Maple, and you get it wrong a couple of times, but then you get it right, and you get this. So the number of 4 by n gram matrices has this rational generating function here with a fairly nice factorizing denominator and a numerator that is not quite as nice. It's just some 15th degree polynomial. We don't think there's much combinatorial significance to the numbers here. Some of them are positive, some of them are negative, but in any event, it gives you the right numbers for the matrices, and that's what we really care about. So from this, of course, you can get terms of the sequence much faster than by brute force. There are implied recurrences. There are asymptotics that are not so hard to work out. And if you were really tenacious, I suppose you could even work out a closed form, because these are only 4th degree polynomials. So if you really wanted some kind of exponential formula, you could get one here, actually, for the number of gram matrices. But I won't bother, because that would, boy, if you thought the matrix would be a whole page, the closed form would be even bigger. So let's ignore that. So this is sort of the end of the story for 4 by n. It turns out to just be this relatively simple generating function. But let me try and tell you a little bit about how this problem would generalize to bigger cases and where we think this process would break down eventually. So if you think back to what we've been saying, nothing has really been that special about 4 rows. Even back to what Delahaye was saying for 2 and 3 rows. Sure, there were some shortcuts. You've got this crochet trick, or in the 4 case, we've got some various connectivity tricks where we say, well, if you saw this, then blah, blah, blah. There's only 2 internal rows. But at the end of the day, there's nothing really special about 4 or 3. We are almost certain that a DFA should exist for any fixed number of rows. Almost certain enough that I would say theorem, there exists a DFA, or for every number of rows, there exists a DFA. There are some problems with that, though. And the problems are that we haven't actually constructed it yet to check that this is right. And here are some of the problems that we anticipate. So problem 1, a DFA for more than 4 rows will have a lot of states, way, way more states than what we saw here for the 4 case.
In particular, we almost had 8 states, but then some of these states, and we only had 1 for 4, the 1010 state, where we had to keep track of, are the 1s connected, are the 0s connected, which of this do we need to fix? And as soon as you have more rows, you have more ways to have disconnected 0s and 1s that you need to keep track of. And we also had to create some extra states for fixing the symmetry business, and that too will create extra states for us to keep track of.
Yeah, in general, we believe the correct states will be something like the current column that you're looking at paired also with all of the connectivity data. And there are a lot of different ways that you can partition entries of a row into, or of a column into connected components. So that will blow up considerably. In addition to that, we have a sketch of an algorithm for how we would actually construct this thing, but because the number of states is so big, because how you determine if an edge exists is so complicated, we don't think that we can really do this by hand. It's not going to be feasible. So we think we would need to write some program to do this, I would say.
Even with 4 by n, we made some mistakes, much less 5 by 2n or 6 by n, etc., etc.
Yeah, so we have some prototypes in the works now, but we're still in the process of doing that. The other problem is, even if we do construct this DFA and we convince ourselves that it's right, the additional problem here, if you want to get generating functions, it's not clear how many symbolic inverses we can really compute anymore. We might end up with insanely large, we might end up with matrices that are, 2000 by 2000 or something ridiculous at that point. And okay, maybe if we're lucky, we can compute some symbolic inverses. So we think we can probably do 5 by 2n, maybe we can do 6 by n, but at some point in the process, this will break down and it will get to be infeasible. And we're pretty sure that no one will ever know how to do 1,000,000 by n, for example. But we hope we can tell you sometime in the near future about at least 5 or 6 by n. So we will report back that information sometime in the near future. But for now, let's stop here. And thanks everyone for listening.
Thank you very much for a fascinating talk. And how do you do the clap or reaction? Okay. Okay.
You did a good enough job, I think.
Yeah. Thanks also for going under time. So we have time for questions, but I have some comments. I think this Gabriel, he meant well, but he set us back. What he did is a different kind of problems, counting this cutting, but decomposes into 2 congruent pieces with reflection and rotation. So 2 different problems. The one, and it's notoriously always harder. And as you mentioned, you need group theory, but I don't like group theory. The original question still makes sense. You not supposed to rotate the 4 by n, leave it as the same. So the only symmetry that I tolerate is exchanging the colors, the 0s and 1s. So there are 2 different problems. So it's possible in the original version, inadvertently, you did some symmetry. Is it right, Natasha? In addition, so that was a mistake to begin with. So it's another problem, just to count them without any symmetry except for extending the zeros and ones or colors. So I
Yeah,
think
maybe we should call them Gabriel matrices. I'm not sure, but
Okay.
it's true. They're all very reasonable problems, and it's similar methods apply to all of them. In this
Yeah,
case.
so it'd be nice to have two sequences for the OIS. One by Robert and Natasha, and one by Gabriel. And Kelly. And the other comment about the feasibility of symbolic versus numeric. X is just one variable, one symbol. So you can do the usual trick, plug in X for many numeric ones, and then interpolate. So
That's true.
manual colors and with Chinese remaining, I think you've been too pessimistic. So probably you can go up to 8 by n, but maybe not beyond.
Okay, 8 by n perhaps. I will accept that.
Okay. Questions or comments for Robert and Natasha?
One way of thinking of your rectangles is they're very special classes of polyominoes without holes. So you might think about the question of less symmetric polyominoes and when you can write them as subdivide them into two congruent sets or other numbers of congruent sets.
I agree. I think this would be interesting, but I don't think that the same methods that we have here will apply, just because we're so reliant on the fact that all of the columns are the same height.
I understand, but this
certainly is something to look into.
This is, you can start with very small sets of polyominoes and presumably do experiments and see if perhaps some pattern emerges. Not that I would expect it to be true.
Yeah, thank you for the suggestion.
More questions to Natasha and Robert? Well, thanks for a great talk and good luck in hopefully having the last version in our paper. Thanks so much for coming. See you next week.
Of course. Thank you. See everyone next week.
Thank you. Bye-bye.